Hello, welcome to New AE's ChipWhisperer tutorial number B3-1. So this is about a timing analysis with a password, and we're going to be doing a password bypass. So how this is going to work is there's a simple sample file we build, and that sample file has, a password check in it. And we want to use power analysis to actually break the password check. And this is all written up. There's some written examples of this. This video will go through everything we're doing. And the thing to remember is that basically we're going to be attacking this this while loop in the password check. So the first step, I'm doing this in the ChipWhisperer VM. So when we use the VM, it's always a good idea if you just got the VM for the first time to do a git pull inside the ChipWhisperer directory, and you'll see any changes. So in this case, I didn't even have the files needed for this tutorial, weren't in the git release that was that shipped with the VM. So unless major things change, the VM image isn't updated just because it's quite large to download, and it's much easier to do a git pull to get the latest version. So what we're going to do is the first thing we're going to do is build the demo code that we're going to be attacking. So the demo code itself lives in and I can start again from scratch if you want to follow along. So from the home directory, we just go ChipWhisperer, and this is where we did the git pull. So you can see it's already up to date. I'm going to go in the hardware directory. Inside that, we then have the capture directory, or not capture, victims directory. Inside the victims directory, we have the firmware directory. And so this is all of the example attacks that you can do against various targets. So it uses a hardware abstraction layer, the HAL directory, and the other ones typically build on top of that. There's a few third-party apps that only build for one specific platform. So what we want to go into is the basic-password check directory. And you can see inside this, we have two files, basic-passwordcheck.c and makefile. So the first thing we want to do is double check that makefile, and I'm just going to use the code editor on the desktop here. You can use other ones if you want. You don't have to just use this. And victims, firmware, basic password check. I'm going to open the makefile, and at the same time, I'm going to open the C file that was there too. So we don't need that. And if you scroll down the makefile, you can see here basically where we set the target device. So by default, it is set to the X mega on the ChipWhisperer Lite. So the ChipWhisperer Lite, if you haven't broken it apart, this you can follow along directly. If you're building for something else, the Arduino or the multi-target board, you can comment those out. So I'm not going to change that. And this is the file that's actually compiled. So what's of interest to us is at some point it does it asks for a password. Please enter password to continue. It reads in the whole password, so the user enters it. There's no timing attack there. In this case, we cheat and we have a trigger event just to reduce jitter in the UART. So it makes it easier when you're first experimenting. You don't need this. And we have a pretty typical implementation of the password check here. So there's just a for loop, and it says, is the password bad? Once it's bad, break out of the for loop. And it's just checking each character at a time. So there's various, variations of how this is done, but this is pretty common. And you'll notice that if the password's bad, it actually adds a random delay it's actually, in this case, the random delay is only random if it kept running it. There's a bunch of bugs in this. It's sort of quasi on purpose, but for example, it doesn't seed the random number anywhere. You should save that the seed in EEPROM or something when it loads. But the idea is that it could be done, and if either way, it actually just goes into a while loop. So you have to reset the system to get back to the password check. So that was sort of another example with things you might see where, if the password fails, there's a long timeout. In this case, it's an infinite timeout, and we'll see how that just doesn't matter. All right, so to build this, all we do is we run make in that directory, and this assumes you had, it's giving us errors here. So to build it, we just run make at this command prompt, assuming we have Avero GCC and everything installed. And you'll see this build results. What's critical is you have this built for platform CW Lite-X Mega. So you need to see those lines to be assured that you've built for the right platform. If you change the platform, it should say something else. All right, easy enough. The next thing we need to do is get some basic communications up and program the XMega device, or AVR if you're using something else. This tutorial will be written as if you're using the XMega. You can do some adjustments if you want to use the Arduino pretty easily. So open ChipWhisperer capture. And rather than in the previous tutorials, you manually would select this, select ChipWhisperer Lite, hit connect. An easy way to get started is we're just going to choose a similar-ish script. So I'm going to use the simple serial on XMega, even though we're not doing XMega. And if you get an error like that, we're using the VM. So what happened is I forgot to connect it through to the VM. So you always have to make sure you have that. And then we see it found it, programmed it, and there's some waveform, but it's not going to work for our system, and in fact you may get something else because you might have had something else programmed in. But this will set up the clock and the serial line and stuff like that. So we'll use the programming tool, and again you can see the other tutorials that go through this, and you select like the ChipWhisperer Lite XMega programmer. Give it a flash file, so we just find the ChipWhisperer hardware. So basically that directory we were in, that basic password check, it created this hex file. And you should always check the time, 1610, 1612, so to make sure that was the right one that built. You can detect it if you want, but you just hit erase program and it'll succeed. You'll also notice up here, again, it's printing when that file was modified, which is to say when you built it. So it's a good idea to get in the habit of checking this matches. Because it can be very frustrating to select the wrong file and then you go like, why isn't it working? If I fix that bug. So that's just a handy thing to check. And now actually leave this window open because we are going to use this to reset the device for now. The other thing we're going to do is we're going to open a terminal, so tool open terminal. And this connects to the serial port that the ChipWhisperer is normally using to talk to the device. So drag this open. Resize that, and all you have to do is hit connect. So now it's listening on the serial port, and we want to reset the XMega device to see what messages come across the serial port. So we just hit the check signature button here. As part of the signature check, it resets the device. So that's what we're using. So you can see it prints up some messages, and these OA in red, by default, the terminal shows non-ASCII as hex and highlights them. So that's because you may not know if the protocol is ASCII or hex, so this way it doesn't get all confused. You don't get weird characters. So you can uncheck that if you want, and it looks a little cleaner. So it says please enter password, and it should say to continue. The buffers in the serial port, it's a very basic serial port, are quite small, and it can overflow it if a lot of messages come across quickly. It's really just used for simple debugging, but we can do enough here. So if I put the wrong password in, so I'll say doggone. You can see there's a bit of a delay. It came back with password fail. Also, the red LED will come on if you have the ChipWhisperer Lite XMega target. All right, and that's it. We're done. So we have to reset the device, and you can see there's a bit of a delay on reset as it does what it claims is super secure looking stuff. So the real password is H0PX3, I believe, and if you send that, it says access granted, welcome, and the green LED will come on the ChipWhisperer. So, that's really it. That's a very simple example of how we send the password and get it back. So it's useful to note for this type of attack, all we really need is some password on the device. So it may be the case that you have a user password and not the root password. But if you can attack the password checking routine with one password you can then apply it to another password you don't know. Or it might be that you can reset the device and get a default password, but it erases all the memory that it's trying to protect. But you can attack a copy of the device. You buy another empty device, you attack it to figure out the vulnerability, then use that on the device you really care about. So don't think, if you're building these systems, don't think that just because, you need one password to do this attack, it's unrealistic. Anyway, so let's keep going here. So at this point, we want to try to get some waveforms when we view this. So we need to make two changes to start with. The first thing is I'm going to switch to the scope tab here, and you can resize this a bit. And there's two changes. By default, this script that I ran used an offset of 1500. We need 0. So that will be the offset from the trigger to when it starts recording. We don't want any offset. You also have this timeout in seconds. We need to increase this just because we're going to be playing around manually, and we need more time than 2 seconds. So the manual says 5 seconds. You could put higher, like 8 seconds, depending how quick you are, and hit enter. This will mean that we have time when we arm the system. It won't time out right away. The final thing we do is the target settings tab. So this is how this simple serial protocol we talked about in previous tutorials actually knows what to send data. So this is where it sends the key. So just delete that. Delete all of them for now, in fact. The go command and the output format. We don't want any of that stuff. So this means that it won't automatically send anything over the wire when it's running. It'll entirely be up to you to send it using the serial port. So now we can do an example, and we can try to get a capture. So what we're going to do is I'm going to reset the target device, so hit check signature. I'm going to type a password example here, so I'm going to put the correct password in first, and we can try an incorrect one after. And I'm going to hit capture 1, and within 8 seconds go over here, click, and hit send, or just hit the send button. So 1, send. So it says access granted, welcome. So hopefully, and you hit view all. The scale was weird because it had I had accidentally clicked on it there, so I just right clicked and hit view all. And so this is the power measurement while it's doing the password check. So what does this really mean? Well, the easiest way to see is let's put in a different password. So let me zoom in a bit, like that. So let me send just the totally wrong password, bad dog. And remember, I have to reset the device, hit capture 1, and then hit send. And you can see here, we see quite a different waveform. It might be more apparent if, let's do this again. So let's send let's send the correct password. Oh crap, I had to reset the device. We hit this, and then we hit send. So that's the correct password, and you can see the waveform looks quite a bit different than a totally incorrect password. And we can see that, let's say if I send an almost correct password, so just the wrong, the last character is wrong, the other ones are all correct. Let's do the same thing, check signature, send. We start to see some, there's parts of it that are similar and parts of it that expand. So what we're actually seeing is that for loop running through in the system. And that's what we want to attack when we do this, this timing attack. But, this is kind of crazy what we're doing here. So let's use the software to automatically send the test password. So in the go command, I'm just going to put the correct password. And I'm going to put a /n at the end, so that's sending the new line automatically. And I no longer have to do this crazy stuff here, so I still have to reset the chip manually. But if I hit go, you can see it's automatically sending the password, in that case the right password. So we can start to play around a little easier and take a look at what happens when we send wrong passwords. And most interestingly, you'll start to see here, as I send one less character being right, you see this loop decreasing in size. So you can actually see the timing attack working, although we're doing it manually. So if I send, just one right character, one less right character here, And you have to hit enter after changing the go command, by the way, or click off it. You can see again, we've lost another entry in the loop. If I send a correct character, we can see that that loop's going through a little further. So we can really easily see how this timing attack works. But we can't yet do this automatically. We want to have this automatically breaking the whole system. And you can see that loop going through differently, but what are we going to do that? How are we going to fix this? So one of the first things we want to fix is I was hitting this check signature button to reset it, and that's kind of annoying. I don't want to have to be doing that, and if we script it, obviously we need it to entirely be doing it auto. So how we do that, I'm just going to move this around a bit here. There's these windows at the bottom. One of them is this Python console, and for all of this stuff, this is where we get more into Python hacking. So obviously, if you have Python experience, it helps a lot. If not, you can follow along, but you may want to do some background reading on Python. So if we type self into the console, it's actually giving us the window, the ChipWhisperer capture, what the class is, which means we can then go open that file and see what's inside it. So when it has here like ChipWhisperer.ChipWhisperer.ChipWhisperer.capture, what you could actually do is you can open the code editor here, and ChipWhisperer.capture.ChipWhisperer.capture actually references a file. So we could say ChipWhisperer, software, ChipWhisperer. So this is sort of the base directory, capture, ChipWhisperer.capture.py is the file, and you can see. So if I just do this here. So this is what it printed, ChipWhisperer.capture.ChipWhisperer.capture. So you see where that is, ChipWhisperer/capture, ChipWhisperer.capture.py, and then the class is the last one here. So within this file, I'm just going to search for, that class. And so this is that class. And what we want to do is we want to reach out and touch the scope, because we're trying to reset the AVR. We need to run that check signature command. And you see right away there's something called self.scope. So a lot of this, if it's not documented, so some of the classes will have members that are documented, some you'll just have to go through and play with. So in this case, we know self.scope is probably what we want, because we want to touch that the programmer on the end of the scope. So self.scope points us to this OpenADC interface class, and we're going to do the same thing. I'm going to go through this directory and see what members are likely to contain the file of interest. So we know it's scopes, OpenADC. I'm just going to search for that class. Within the class, we can sort of go through and look at where does it set the, oops, this is the wrong class. This is some other class. You've got to be careful of that, because if they have a similar base name. Okay, here we go. So here's the actual class of interest. And we can see right away there's this self.scope type. So the naming might be crazy, and it may change slightly if the software has been updated. But that looks promising, so I'm just going to go ahead and see what that is. And we can see it's this, it's in the same file, so I shouldn't have closed the file, NAE USB chip. Okay, so OpenADC, and let's find that class. And again, be careful not to get confused. And if we sort of start looking, is there anything useful here? Right away, we see that Xmega. So we can see this is where that, we had this ChipWhisperer Lite Xmega programmer dialog in the tools menu. Clearly what it's doing when I click that, it's opening this object here, because we see that same name. So some of the other hints, of course, is you can just search for, if you say, well, I want this programmer dialog, just search for the name and see where it is, and figure out how to access it. So we want let's use the Xmega dialog. So ChipWhisperer Lite Xmega. So we're now going to go self.scope.scopetype.cwlite Xmega. And we can now see where is that defined. So capture utils xmega programmer, and we're looking at the programmer dialog window. So ChipWhisperer capture utils xmega programmer, and I'm going to look for that class. There we go. So all we need to do is we're just faking that check signature button. So we can see the buttons right here, and right under it, it says, when it's clicked, it calls the read signature function. So let's look for where that's defined. And all it does is it checks for the device and closes it. So it appears all we have to do is call this function, and we'll do the same thing as if we click that button. So let's try it. Read signature. Did it work? I don't know. So what we have to do is look at the terminal. And we can see that it did in fact reboot the target device. So we now have an API call which is capable of resetting the device. So that's the first step towards getting this all done automatically. Now, the next step is to use something called the auxiliary module. So one of the module types that wasn't set, there's these modules that do other stuff. So if you need to reset a chip or toggle pins, you can do it through the auxiliary module. We can also add our own entire module in. So the first thing I'm doing here is I'm doing this through the command line here, which isn't as easy. Often you do it as part of a script, but if you do it through the command line, you can play around a little more. So I've got to do a few imports here. So I'm going to import the sleep command, and I'm going to import what's known as this auxiliary template. So again, they're all in the written guide there. Is a little easier, but if I go from time, import sleep, and I can now call sleep like for 800 milliseconds, and you can see it sort of delays there, or 2 seconds. So that's all that command is doing. I'm also going to import this template. So this is one I just know is needed. And how would you find that out? You could look at some of the existing templates to see how they work, or some of the existing auxiliary modules. So for example, I might say software capture auxiliary, GPIO toggle. How did they define everything? And you'll see right at the beginning, all it's doing is it subclasses the auxiliary template class and then overrides some of the functions. So stuff like trace done is called after every capture. So if I hit capture 1, it does the capture and then calls this afterwards. And trace done is where we want to do the reset, because that's, we've sent the password, we've recorded the waveform. At this point, it's spun into an infinite loop. Okay, so I'm going to import the auxiliary template like that. Finally, we have a little, so what we're going to do is we're going to make a tiny little function here, and it's going to be called reset device, and this is all the function it's going to do. So I'm going to show you how I enter this through the console directly, as if I were sort of doing this in a interactive fashion, and we can do this. So I'm going to do the first line, define reset device, and have the colon is key for it to catch on this. And what you'll see is this little, these 3 arrows here turn to dots, and it's now expecting the next line. So I have to indent this line, so hit space twice, self.scope type, and this is where the previous read signature function we tested is being used. So you can confirm there's no typos. And then I want to sleep for 800 milliseconds. So why I have this delay is just that once it resets, it prints those, startup messages. So I need to make sure it has time to print them all. You could, of course, wait for it to actually say, please enter password, but I'm not going to do that. I'm just putting a simple delay in. And I know it takes about that long to print the messages from previous experiments. And we still have 3 dots, so you have to hit enter so it knows that you're done defining that. At this point, I should be able to just call reset device and check that works. Oops. If not, obviously I have some typo there, so let's define it again. We'll do the same thing, and what you can see is I forgot self.scope type. We add the sleep, and then enter. Let's try that again. So if I call reset device, did it work? Well, let's check. Yep, so obviously it is in fact resetting the device, so that's great. And it's losing some of those startup messages because that call to sleep, it's not flushing the buffers on the chip, and as a result of that, it just drops those messages. So, oops, but doesn't really matter for our purposes. We don't care. All right, so we're most of the way there. The final thing we need to do is we're going to be defining a class. And so this class is this reset class, and it uses the auxiliary template just so we can patch it into the entire system. So in the similar manner, we're going to define that through the console. So class reset class auxiliary template, and don't forget the colon. Again, it changes to ... Be careful of the indent format. So it expects one level of indent, and it's going to be expecting another level of indent. So the first one is this trace done. So trace done is defined in auxiliary template, and I'm overloading it to call my reset device function. And again, it now expects another level of indent. So in this case, I'm using 2 spaces and 4 spaces. You can use 1 space and 2 space, whatever you want. So call reset device. And that's it. And then hit enter again. Finally, define an instance of that class, like that, and check it works. Oops, so we call trace done as if it was called. And that should be resetting the device. So once again, let's just confirm. All right, so the final thing to do is we just patch it into the auxiliary module. And to do this, you go self.aux changed. So this is what's called normally when I change that GUI setting, and I'm just going to pass it RC. And there we go. So now if I hit capture 1, I should see, you can see basically I'm getting these waveforms here. Let me just change the size around a bit. So I'm getting these waveforms here. I no longer have to reset the device, and we can now, I can add, oops, and don't forget to hit enter if you change the go command, otherwise it won't take effect. So you can see, hey, I can play around with what the password is and not have to do any funny business. So at this point, now that we can play around, what we need to do is figure out how we're going to determine how far in the loop we got. So a few things to remember. What we're looking at, let me open this file again, is in the password check, we get a trigger, and we are trying to figure out how many times through this loop we ran. And we can see through the power analysis that if I, for example, if I ran all the way through the loop, I see 1, 2, 3, 4, 5 runs. If I change the password so it's 4 runs, we can very distinctly see this change. And we need some sort of indicator of what point we want to do the run at. So the trick here, so if you look at, for example, we want to detect where some area of the trace is. An easy thing to do is let's just look at, here's where the loops are being inserted in this area here. Let's just look at some of those traces that appear to be sort of moving along. So if I put HOP in, we can see like this sort of negative point here might be a really easy one to monitor. The exact point is going to vary depending on the compiler. So as a warning, for example, if you go through the tutorial, it's talking about 0.153 and 0.225. This was for a version compiled on WinAVR, which has an older AVR GCC than if you use the virtual machine. You might get differences too for your specific hardware. Variations within the phase of the clock will adjust what these waveforms look like, and that will mean you might get a different point where you see this really big negative peak. But what you want to figure out is where is that nice negative peak and how does it move. So let's look first. If I send the completely wrong password, so I send A, that big negative peak there, which we can pretty easily find, is at 0.189. And now let's look again. So right now it's at 0.189, and let's move that peak over one character. So I send one right password, or the first character is right. It's now here at 229. So it's moved over just a little bit, and we can write down, just start a new file here, 229. And let's again send just the wrong password. And you can see it was right there at 189. So it would appear that it's moving over by some amount every time. And if you just subtract the two, you'll get what the delta is. And what we're curious is this reliable? So in this case, the delta is 40 cycles. So for example, if we do 189 plus 40 times 4, this should tell us where the peak will move if we send 3 right or 4 right passwords. So 189 plus 40 times 4 should give us 349. So let's see if that is reliable enough. So let's HOPX. So there's the big delta, and 349. That's what I said, wasn't it? Yes. So we can reliably, if we can find that delta, we can figure out how many of our password values were correct. And nicely, it's sort of the most negative peak. So all we really have to do is check what the value is at, the predicted point, and see if it's below some threshold. So how are we going to do that? We're going to do that through a script. All right. So before we get to that, what we need to do now that we have an idea of what we're going to do, we want to make a script that runs everything for us. So to do this, we're going to make a copy of one of the existing scripts. So if I have this ChipWhisperer software, ChipWhisperer capture scripts, this is where the example scripts are. So ChipWhisperer Lite dash simple serial X mega. If you're using a different target, use a different base script. And I'm just going to copy this somewhere. Let's make a new folder, lab demos. And I'll just put it right there. And I'll rename it right away so I don't get confused, because I don't want to edit the wrong file. Password crack. And we open it with our editor here. So one thing you'll notice is that there's all these commands in the script. Where do these commands come from? That's part of the ChipWhisperer scripting. They come up as these script commands. So every time I'm changing something, it's actually printing these script commands here. And this makes it easier for you to, if I modify something in the GUI, I can see what commands I have to send to cause that effect through a script. In our case, all we really need to do is we'll have to change some of these settings here, but don't worry about that yet. For now, you can sort of just take a look at how it's all related. But before we do that, let's begin by just checking the script works at all. So I'm going to go ahead and close this. Come on, there we go. And save this script. And I now want to run that script. So I'm going to, in my console here, CD to wherever I saved it. and just run it with Python. And what we're checking here is you might get this error. It says, no attribute, something like that. What this is if the FPGA program fails to work, you get a bunch of really weird errors like this. And all it needs to do is there's a default that needs to be changed. To change this default, we run the example script before, any script that connects properly. We then go to Tools, Config, ChipWhisperer Firmware. Oops. I think that was the old application I closed. And all we need to do is, so this directory here, you can see uses a reference to where it's looking for this file, this ChipWhisperer Lite firmware. We need to turn that into a absolute directory, not a relative. So it's really easy to do. Just hit find, go ChipWhisperer, hardware, capture, ChipWhisperer-Lite. If you're using the Rev2, obviously don't point it to this firmware, point it to the Rev2 firmware. And CW Lite firmware. So it's the same directory, but now it's absolute and no longer a reference. And if we close that, it automatically saves it, and we should now be able to run the demo. And the demo, you can see now, connects fine. Everything was loaded, programmed FPGA. So the issue before is just that it wasn't programming the FPGA. So all this did was this just got us back to where we were starting from. We want to do a few more things. We want to edit the script a little bit. So open the script. The first thing we need to get rid of is this trigger offset. So it was set to 1500. If you remember manually, you set it to 0. Now just do it through the program. The other thing we want to do is erase the commands that send some default text. So if you remember before, I'm going to run the script again. Under target settings, there's this load key command, and we erased it. And we erased the go command, and we erased the output format. You can see down here it prints, these. It printed these new script options. So I'm going to copy them with Control-C. And actually, you can close that or you leave it open. And I'm just going to paste them right here. And all I want to do is append them to this Python list. Again, be careful with Python being white space sensitive. Make sure it lines up. And add the commas at the end. Otherwise, you'll get an error as well. So I added the commas, added these. And now if I were to run the demo, let's do that. What you'll find is that it connected, but it erased those key commands. So that's perfect. We're slowly getting there. The next thing we really want to do is hack in that previous auxiliary module we had. So how do we add that through the script? And we can sort of take advantage of Python's ability to be very, hacker friendly, in that we're just going to more or less copy and paste what we did previously and throw it in here. I'm just going to delete some of this, this other stuff here. We don't care about the number of traces. So yeah, after the point that it downloads all hardware, I'm going to write my modules here. Before we do that, we have to do 2 more imports at the top. So down here, I'm just going to go import or from time import sleep. So this was the same commands we used on the command line from ChipWhisperer.capture, dot auxiliary, I believe. Auxiliary template. Import auxiliary template. So you can see it's starting to autocomplete for us, which is sort of nice. So that gives us the imports, and we can actually, so within Python, we can do some interesting things here. One of them is we can just define these new functions. So define the reset device function, and it's the same thing as I typed in the GUI window. So you can copy and paste that, or you can look at the the details on the follow along guide, and then I'm going to do that sleep 0.8. And I can even do a class definition here too. And we're using the auxiliary template. And within the class, oops, trace done. We're just going to call the reset device. All right, so we now need to create an instance of this. RC equals reset class. And if you want, you can make it follow slightly more Pythonic approach. And we're now, as before we did the aux changed, rather than doing self, I'm just doing cap. So cap is the capture window. Changed. All right. So in theory, we should be able to now open this script and it'll just connect. The one thing we want to do is we would like to set a password. So let's just run it. So if it gives us an error here, what's the error? It's indentation. Should work. So what it might be is if there's so there's a combination of tabs and spaces in here. So we should change this to use spaces instead of tabs, as everything here is, all these files have been using spaces. So you do have to watch out a bit with Python, it can get you. So just if you change your editor from the get-go to use spaces instead of tabs, that shouldn't be a problem. So we can see the errors over mean it's tabs, and when it's the dots, it's mean it's spaces. So that's all I'm doing here, is getting rid of that so it doesn't throw it. All right, so now it worked. So it can connect, and it's not doing anything because we didn't set a password to send it, so it's not actually triggering. So let's send it a password. That's the wrong password. Here's the right password. And we can hit capture 1 and you can see it is working. So now what we can do is we can use the target connection, the script command here, to figure out how we set this automatically. You'll notice there's an extra slash. That's because it has to, the way this system's working is it's sending this command to the GUI, and then the GUI sends it over the serial port. So we do need the extra slash to for this to work, and we can just call something like cap.setParameter, for example, and you simply paste that in. So this would automatically set the password to what we're expecting, which is pretty cool. So we are more or less now ready to do some sort of automatic attack. So I'm going to first define what the list of characters is to try. And all I'm going to do is, at this point, I'm just doing all lowercase because I know that it's all lowercase in the example I'm using. Obviously, if you can cover all of lower and upper, it just takes longer to go through the example. So I have this try list that has all the characters. Oops. And I don't know if that's all in correct order or not. You can go through if you really want to be fancy here. Doesn't really matter. So what I'm going to do is I'm just going to go for character in try list. Let's set the password to whatever the character is. And I'm just going to use the one character right now. So I'm just going to try to crack that first character. And we can see there's this below, this capture 1, oops, is what actually runs a single capture. This other PE command you sometimes need, so PE is processing additional events that have occurred as a result of the GUI. So it's useful to throw it in. If you're using the set parameter, it automatically does that, but if you're calling the API, you need that. So let's print what the try is. Try equals. So it's not doing anything automatically, but it should be trying a bunch of passwords, and we can view the results. So let's do that. If I switch to the debug logging, you can see try A, B, C. And what I should see is when it becomes H, I want to see this jump over. You see that? Okay. So it jumped over for try equals H. And it's actually going to keep going, so just hit Control C to exit it there. So we now need to detect that automatically. And how are we going to detect that? Basically, we can access the scope data points through cat.scope.datapoints. And if you remember before, I said what I'm going to look for is at point 189 is the starting point, and then there's a delta of 40. So let's just print to start with point 189. And we should see that for the correct try, that value changes drastically. And again, change the debug logging tab, and we see, A, B, C, D, E, F, G, H. Oh, yeah. So you can see for the correct try, I can't stop it without killing. For the correct try, the printed value was much, much smaller than for incorrect tries. And so that's exactly what we wanted to see, is we are now able to somehow automatically detect when we've gotten the correct one single character of the password. So at this point, we can more or less expand this a little to do our full password. So I'm going to record what the password is, as I break it. So the first thing I have to do is I actually need to send the known part of the password plus the unknown part of the password. So I'm going to send it the known part of the password and then add the unknown character in. Otherwise, it obviously is only going to ever crack the first character. And we've got to do a range here, so I'm going to go say for I in range 0, 5. Right now, it's very basic. I just tell it how long the password is. You could obviously detect... finally close, yes. You could obviously detect when it comes back with the access granted message. I don't check that right now. Alright, so it's going to print the try, and we don't want to print the data points. What we're going to say is if the value of those data points is greater than, you saw it was normally around minus 0.2, so let's say it's bigger than minus 1.5. We have figured out what the password is. And I'm just going to say print character number equals whatever the value is. The other thing we need to do is, you remember we had this offset of 40 cycles. So 40 cycle time, whatever the character number we're attacking is. And if we find it, add it to the password string and then break. We're also going to detect if we get this far and we're checking character 9, it means character fail. But to keep the attack going, I'm going to add a blank incorrect value here. So the attack won't continue past this point, actually, because for the attack to work, it has to break each password in sequence, because at this point, the target device will have jumped out of the loop, but for now, it's simple enough. You can clean it up later if you want. So in theory, that's about all we need to break the password, but let's try it. Maybe there's a bug in here I'm not seeing. It's rare when things work magically the first time. So if this works, it should... So it found character 0 is H. And you can see it's now generally always finding... it's always sending the correct beginning character, so now it's trying to break the next one. So the next correct character is 0. So it'll have to cycle through a little bit. And this is so slow because it has that 800 millisecond delay on startup for all the print messages. So there it worked. So you can see character 1 equals 0. And the next one should be P. So that should come up here. So that worked. What do we have next? 3, I think? No, X. X and then 3. So I forgot to add at the end, it should print the whole password. So it doesn't have that feature. You can add that to the script though. There you go, O, X. And the final one is character 4, or 5. It's using 0 base. For this count, should be 3. And if we get that, it successfully broke the entire password. Remember, it resets it. That auxiliary module always resets the device. So you won't see the, if you wanted to see the green light go on or something like that, it won't happen. And you'll never see the red light goes on because it resets the device before it even has a chance to. Oh, you saw it there for a second that completely changed. So for some reason, that final one actually failed, even though you saw the system working up to that point. So I don't know what happened there. Let's just take a look out of interest. So what it might be is that one of these values needs to be slightly tuned. So if it does 189 plus 40 times 4, what's the point it's going to be looking at? 349. So let's go look at point 349. That's around here. Ooh. So the problem is that in this case, what's actually happened for that last character, the point we're looking at, if we pull up the software, is, so if the password is bad, it does this other, random loop. So we must have been attacking a point here. We're looking for, hey, let's use that for the timing attack. When the password's correct, it does a completely separate, code through. It just prints this. So we didn't even see, we waited too long. It already had started doing some other process. So the final character, you have a few changes. One thing you could do is you select a different point. So maybe like this point here at 340 would be repeatable. And we could use that. Or for the last character, obviously isn't a big deal because you don't have this issue of, you get a response back that tells you that it is correct. So you don't really need to do the power-based timing attack for the last character, even though we did. So you can see here where we were attacking, changes. We were attacking around here, this point, and when it's right, it no longer shifts over. So you might need to select a different point as your reference or something like that. But that shows you how the timing attack using power analysis can be done with the ChipWhisperer and using the ChipWhisperer Lite target example. So thanks for watching. If you have problems or questions, please add them to the forum.